Hello, all of you. Today is a bit different in the seminar. It's the first of our two planned oldies but goodies sessions. We asked for volunteers. Do any of you have an older piece of work that never garnered the attention it deserved? And we had 8 responses. So today we'll hear from Jean-François Laslier, Mark Wilson, Jérôme Lang, and Hervé Moulin. Given the special nature of today's session, I invited the speakers to feel free to shed the normal garb of academic modesty and speak more directly to what makes their results interesting or important, but only, of course, if they felt comfortable doing that sort of thing. Each speaker will have 10 minutes to make their case, plus 5 minutes for questions. If you have a question during the talk, of course, you chat question in capitals into the chat, and we'll make sure the question gets asked. There'll be a coffee break after the first 2 speakers, and you can find the bibliographic references on our website. The first speaker, Jean-François Laslier, will talk on a paper with Gilbert Laffond and Michel le Breton, K-player additive extension of 2-player games with an application to the Borda electoral competition game from Theory and Decision 2000.
Okay, shall I go?
Yes, go.
So, can you see the screen? Okay, so this is a really old piece of work because I checked the last version before publication was 95, so that publication was not fast even those days, and that makes 27 years. Wow. Okay, so because this is speed dating, I will go very quickly to the poem. So here are some pieces of notation, general notation for normal form games, K-player normal form games, S, capital S, set of strategies, and capital J, the payoffs, or capital J or small j, by the way. Mixed extension are as usual. And we will, in particular, consider symmetric games in which players have all the same role and the same payoff functions, of course, up to permutations, and zero-sum games. The sum of the payoff is 0. So here is the original notion in this piece. Consider a symmetric 2-player game. Okay, so X, the set of strategy in this game, and G is the payoff function. Consider the K, capital K player additive extension as the games, the K player games, in which each of these players has to use the same strategy against all the K-1 opponents with whom she is playing this 2-player game. Okay, so it's very simple. The payoff in the additive extension of the game is a sum of the K-1 interactions. Okay, so the first small remark, very easy, is that by linearity of mathematical expectation, the mixed extension of an additive extension is identical to the additive extension of the mixed extension. Computation is obvious. Now, we are interested in games, so the basic games, the symmetric zero-sum games. The symmetric game, the 2-player game, is zero-sum. The theory of zero-sum games is very specific, as you know, and equilibria of these games are interchangeable, meaning that the set of Nash equilibria is in fact a product of the set of optimal strategies. So I denote by capital M the set of optimal strategies in the two-player zero-sum game. Therefore, the equilibria are all the pairs of optimal strategies. If x1, x2 is an equilibrium, so is x1, x1, and x2, x1, and x2, x2. Okay, so this is perfectly well known. So here is the small theorem in this paper. If a symmetric zero-sum game has a unique equilibrium in mixed strategy, then this equilibrium is symmetric. This is well known. Call it x star, x star. And its additive extension, the additive extension of the two-player game, has also a unique equilibrium, which is each player playing x star, x star, x star, x star. Okay, so this is a nice feature. In fact, when I read again the paper, I realized that I was putting that we were putting emphasis in this paper on the uniqueness property, but that maybe was not very a very good idea, because in fact I think we have a more general result, that is the set of strategy of the additive extension is just the product of m k-fold, m to the k. So the zero-sum assumption is essential for this result, and here is a very simple example. This is a kind of paper, rock, scissors game. It would be exactly a paper, rock, scissors game if on the diagonal there were 1/2 instead of 0. Okay, so it's a paper, rock, scissors that is made non-zero sum, because if you play the same strategy as your opponent, you lose. Okay, so in this game, you see, in this game of pure strategy, the payoff, the best response structure is the same. So in pure strategy, this game has no equilibrium. Okay, this two-player game has no equilibrium. But for 3 players, okay, if you have 3 players and you play like in this additive extension, you have to use the same strategy against your 2 opponents. Okay, then there is a possibility of 3-fold coordination. Each of the 3 players playing different one of the 3 different strategies. Okay, then the payoffs are added. Therefore, each player is receiving 1 unit. Okay, 0 against one of the 2 opponents and 1 against the other. Okay, and that's really the best that this player can hope. Deviating certainly will not help. Therefore, this is a pure strategy equilibrium. And there are 6 such equilibria, because you can assign the 3 roles to the 3 players as you want. Okay, so this is a specific feature of the zero-sum games, that in the additive extension, there is no such k-fold coordination that pops up. Now let's come to what we can deduce from this little remark for the border count. So imagine k parties, political parties, they compete by announcing policies. So xk is announced by party k, okay? And there is a preference profile. There is a set of voters, okay? There are preference profiles. Pi is the preference of individual I over alternative, the strict part. And when receiving the the messages of the parties. Each voter votes according to the Borda rule, okay? Of course, we have to take into account the fact that some proposals may be identical, okay? So we do it in a very natural way, okay? And therefore, this provides the Borda count for each of the party, okay? And we define the electoral competition game among these parties as the K-player game, in which parties have a strategy space of the set of alternatives, okay? And the payoff, given what what all parties are doing, are provided by precisely the Borda count, okay? Up to some normalization, this is a zero-sum games because the sum of the payoff to the parties is clearly constant. And a short computation that is, again, due to the linearity of the Borda formula, shows that this payoff can be expressed as a function of the pairwise comparison that the voters do between the proposal of the parties. Precisely, if we let delta K and K prime for individual I and proposals X being equal to -1 or +1 or 0, depending on whether the individual prefers what party K proposed or party K prime proposed, we see that with a simple sum, we can write down the payoff function in our electoral competition game with these variables. Now, the net plurality that belongs to the realm of majority voting, which is for any two proposal, how many voters prefer the first one minus how many voters prefer the second one. This is little j of xk and xk prime, okay? This can also be written as a function of these small deltas. And in fact, we see very easily, it's a very almost trivial computation, that this K-player game, the Borda electoral competition, is precisely the K-player additive extension of the two-player case. The two-player case is the two-party electoral competition for majority voting. Okay. So to sum up, the K-party Borda competition is the additive extension of the two-party plurality game. Okay. What can we conclude for that? And that's the conclusion of the paper. So we know that the two-party electoral competition game has a unique equilibrium in mixed strategies. And this equilibrium coincides with the Condorcet winner whenever the Condorcet winner exists. Two parties who compete for the votes of the electorate will end up proposing the Condorcet winning alternative, both of them, if such an alternative exists. If not, they will randomize in a particular well-defined way. We conclude that the same is true for the Borda competition. Therefore, if we take into account these incentives of the political parties, Borda and Condorcet are the same. This is a funny result. And I was thinking when we noticed this result that this model might serve as a benchmark model for the study of multi-party competition. Because multi-party competition is very little, there is very few research on that topic. And it would be interesting to work out both the objectives of the party in such a competition, to see if the objectives of the parties depart from the border count in one way or the other, maybe putting more or less emphasis on having a more or less vote in a non-linear way. I don't know how the result will change. Same thing for the voters' behavior. Depending on the voting rule, we may think that the model of the border voting may mimic more or less a voting rule. I don't know. And all these questions are, of course, completely disappearing from the exclusive study of two-party competition. Therefore, I believe that this little model that I proposed might be a point of departure for this study. That's it.
Thank you, Jean-François. Let's unmute briefly and give Jean-François a round of applause. We have time for a few questions. I don't see any questions. Oh, here's a question from Adrian in the chat. Adrian, you want to ask your question?
Sure. Yeah. So I might not have understood it completely. So I just wanted to check. There's these polymatrix games where you have a network and each edge, the two endpoints of the edge, the players play in the simplest game, they play a zero-sum game. And the strategies of each vertex have to be the same for each edge they're playing. And more generally, the edges don't need to be zero-sum games. It could just be that whatever strategies they play has to be zero-sum in the entire network. So these sound really similar because you're picking the same strategy. You know, you've only got allowed to pick one strategy against each of your other sort of pairwise components. And there's a lot of results there, I think, on sort of showing that maxi-min results still hold, that these things still exist and are computable. So I was wondering if there was a link.
Apparently, this is what I am doing in this paper on a full, on a complete network.
Yeah, that's what it sounded like. Yeah. So I think that's, if you're not sure, if you're not aware of it, there was a lot of recent results in 10, 15 years ago on networks that weren't cliques. Yeah.
Okay, so maybe these results were not aware of this one.
Yeah, I suspect they weren't aware of your work. Yeah.
Are there other questions? Yes, Hervé.
Yeah,
you have to unmute.
Thank you, Jean-François. In terms of interpretation, can you think of slightly non-voting context, but different types of contest in which having the border count as your objective function would make sense? I mean, I don't know. I haven't thought through that, but firms are competing for customers who assign them points, and points means some specific amount of money. You see what I mean? Yes. It seems, because in the political context, it's not very obvious to think, my objective function will be my border score.
Well, there are two things. One is as to the objective of the parties, and one is as to what the voters do. Here, I explicitly stated the hypothesis that the voters are asked to submit a ballot that is a ranking, and this is counted according to the border score. But in fact, the linearity of the border count makes it possible, I think, to imagine other models in which, for instance, people would vote for one party and only one, but with some probabilities that is related to how much they like the parties. Okay, and if there is a simple model that explains that, okay, you would at the end get the same thing. Okay. So from that end, it seems that the border, and that is more general, in fact, from that end, it seems that counting ballots according to full ballots, okay, may be a reasonable model for other electoral behavior of the voters under other rules. Then, with respect to the objective of the party, the objective of the party is the border count of the party's proposal. Again, it's a bit the same. We may think that the border count is something that takes into account the amount of support that this proposal is receiving in a reasonable way, in a sense, compared to the others. Okay, so I'm sure that there will be many models that will be either partly depart from that or resolves to the same thing under some mechanism of how does the party evaluate its fate on a market in which the market shares are this and that. Okay.
Okay. Thank you.
Thank you, Jean-François. I think that to keep on schedule, we should probably move on, and I'm sure JF will be happy to hear from those of you who didn't get to ask your questions. So maybe you could quit sharing screen. And Mark, you're on. So our next speaker, Mark C. Wilson, will speak on a paper with Geoffrey, Pritchard, and Reyhani, Power Measures Derived from the Sequential Query Process, Mathematical Social Sciences, 2013.
Unmute. Yeah. Okay, thank you, Bill. Thanks to the organizers for including me in this session. The name of the session not only describes the papers, but also the authors, I think. Although I was a little worried when I heard us described as distinguished, then I realized that maybe I'm distinguished in being relatively undistinguished among these distinguished colleagues. So in any case, we'll go on with it. I defy anyone to find a more obscure paper than this one. It's my last paper ever with Elsevier before I started boycotting them. And it has 2 citations on Google Scholar, both of which are by the authors. So let's see. So I start with just basic terminology, standard terminology on a TU, transfer utility game, type of standard cooperative game. Simple game being a special case of that, where you have either winning coalitions or not winning coalitions. And I'm using this notation to describe the marginal effect of adding or taking away someone from a coalition. Imagine that you start just randomly sampling from the set of players, and you just keep going until you've finally got enough players to have seen a winning coalition. Because I define these games to be monotone, once you have a coalition, throwing in extra people, a winning coalition, throwing in extra people doesn't hurt. So just keep going until you get a winning coalition. Right? And we'll call that, if there's n players, we'll say if you don't get one at all, if there's no winning coalition you ever find when you've gone through all the players, then we'll say that the value is n plus 1. This is a random variable, and the expectation of it turns out to be the formula given there. These are simple calculations. Right? We want some kind of a measure of how easy it is to find these coalitions. So we need some kind of rescaling of this to make it look better, because we want a value of 1 if everything is winning and 0 if nothing is. And so we can use some function which is basically measuring the tails of this probability distribution of Q. I'll omit the details there in the short, but it's very simple. So we rescale it by some arbitrary function with a few simple properties. Here's an example of why you might want to do this. We originally were motivated by the idea of measuring manipulability. I spent a lot of time looking at whether voting rules are manipulable or not under various probability distributions on preferences, but for a given profile, most people just use the simple indicator, whether it is or is not manipulable. It could be individual or coalitional or however you want to talk about it. Coalitional manipulation, we did write some papers where we talked about the average size of the minimum manipulating coalition. But that one is much less overlooked. So that wasn't worth talking about. But in general, the size of the coalition is not so important as how easy it is to find them, we thought. So we wanted some kind of measure to see how likely it was that maybe that manipulation would occur. And this query model is one idea. I'm going to have a concrete example, which you'll see in a table later on. It's just very simple. Border rule, you got 4 voters, and those are the sincere preferences. Yeah. So this process of querying and then rescaling, it actually, you can describe it very easily as you choose a probability measure on the sizes of coalitions, you sample from it, and then you choose a subset of that size uniformly at random. That turns out to be equivalent to what we're doing. And this function that I defined before, which was the expected value of the rescaled querying thing, you can think of it as a measure of decisiveness. Or there's a paper by Coleman, an old one, that defines a particular measure. So it's called something like the ability of a collectivity to act or something like that. It's not as well known as it should be. The marginal functions of these things always give you what you think of as a power index, or we'll see in a minute, as a value for the TU game. But for the simple game, you think of it as a power index. If you do this to Coleman, you get the Banzhaf index, which is well known. Now, the simplest functional form of this rescaling, it just jumps out at you. It's a linear rescaling. It corresponds to choosing the subset size uniformly on 0 to n, and that gives a new measure. It hasn't been seen before as far as I know. You can interpret it in terms of what I say here. It's the expected fraction of queries that you save when you try and find a winning coalition. One can generalize the whole thing to TU games, and I've just put some formulas and everything works. And that gives you, the second one gives you what's called a value or an allocation, like, for example, the Shapley value being the most famous one. An allocation of, it's usually thought of as the, you've got a surplus to give out and you somehow allocate to individual players. So these are the details here that you get for the 3 examples that I have there, the 2 known ones and the lesser known one. And the only difference between Shapley and the new thing is that you choose uniformly where you allow empty subsets in the model. Okay, that corresponds, I'll tell you in a minute what that corresponds to. And you can see the specific numerical values for that voting game. Well, at least they're not 0 or 1, so they give you something else. How does it connect? Well, usually in the Shapley value, you think the grand coalition's sort of always winning somehow, right? Well, it's got some certain surplus that you're trying to get, and you want to divide everything up. But in simple games, for example, manipulation, it could be possible that no manipulation is possible at all. Right? Manipulation requires some constraints on whether players have incentives. And it could be that it's just not possible to change the winner at all in any incentive compatible way. And so the grand coalition may not be winning, and that corresponds when you rescale to choosing 0 with some probability rather than just Shapley, which only has size 1 and above. And if we allow this and we change our model of a game, TU game, in this way with this very small change, those functions that we've defined are exactly the analog of what are called semi-values, which are well known in the literature. Shapley is the most famous one, but there are plenty of other ones. They were all characterized, as a slight typo there, Weber doesn't have a final E. They characterize those axiomatically, and you get a very similar axiomatic characterization. You have to make a different normalization. And so you get the exact analog of the Shapley value, which has a lot of applications, as we all know. So in summary, I think there's an entire class of power indices, values, collective measures, which needs to be explored. You could try to axiomatically characterize each one of them by putting in specific one extra axiom to pick them out. I think that this Q0 star, whatever I called it, and the individual version of it could have new applications. There's a lot of talk at the moment about, a lot of people are using Shapley value in machine learning, right, to try to understand the relative importance of various features when they are doing prediction. And, you know, why the Shapley value and why not some other one? Seems like the first thing that came to my head. Maybe there's some options there. And also, if you want to discriminate between simple games, like in some way, how decisive they are, some voting games, for example, I did a small amount of investigation numerically, and this new value seems to be better in discriminating between them. So it's very rare that it gives the same value to two non-isomorphic games of the same number of players. So I think it should be studied more. Okay, that's the end of the talk.
Okay, everyone, let's unmute and give a round of applause to Mark. And we're open for questions. I don't see any questions in the chat right now. Does anyone have a question?
It's destined to remain obscure then. I think that really is, there's some ideas there that are definitely worth looking at, and some low-hanging fruit for people if they want to get into it.
Mark, I didn't have a question, but I did have a comment in terms of the last point you made about being more discriminating among simple games. Of course, the question is whether the discrimination is a meaningful one or not. So
Indeed.
I think it would be helpful for people to see some concrete specific examples where you can argue convincingly that the discrimination, additional discrimination, is compelling for these examples.
Yeah, there's one example in the paper that I don't know how convincing it would be, but at least it's worth looking at. And you'd have to do more. Yeah, I didn't go further than that in this presentation and calculate anything else, but I do think it's worth looking at. It also seems surprising to me that this had not been noticed before. I mean, that this is a paper, as I said, which had no citations, and yet the referee reports were very positive. So I think there is something there. But anyway, I'll leave it to people to take it up if they feel like it.
Do we have other questions? Okay, Dominic, shall we move on to the coffee break? You're going to put people in discussion rooms?
Yes, breakout rooms. So if you want to meet people and chat with people, you'll be put into a random room, and it's always fun. So see you there.
Okay, welcome back, everyone. Our next speaker, Jérôme Lang, will speak on a joint paper with Chevalier, Mordet, and Ravi Abadi. Sorry about that French. Compiling the votes of a sub-electorate.
No, Bill, it was almost perfect. That was a 2009 paper that we liked actually, and that did not get a lot of attention. So there was subsequent work by Jérôme Lang and Vince Conter, which I'm going to cite, but this one either did not get much attention. What is compiling and why should we do it and how? Okay, so I'm giving two contexts and that come with their different motivations. First is time. So sometimes the set of votes does not come together all at the same time. It can be the case that you have some initial votes that you already have, and that you have missing votes. If you have organized a doodle poll already, you know that some people don't vote on time, and so you may ask the question, I mean, how can I summarize the information that I have so far so as to prepare the ground for the time when I have the rest of the information, okay? And of course, I mean, the requirement is that I should still be able to compute the solution to apply the voting rule. And space, so maybe space is the motivation I would put forward now, as opposed to 2009. Suppose that the electorate is split into different districts or different voting polls, and each voting poll or district counts its ballot separately and sends the outcome to the central authority, like the ministry, which determines the final outcome. And you ask, I mean, which is the minimal information that each district should send to the central authority? Why is it important? Well, it's important for verification. You know, I mean, if you are in a voting poll, there are a few thousand ballots, and there are observers who can check the ballots. You can check that the scores that are published are indeed the true scores in the voting local poll, and then local results are made public. They are published in newspapers, and they are sufficient for checking the final outcome. But of course, I mean, the size of these local results, the size needed to store these, to publish these local results is important, because if it's too big, it's impractical. Okay, so what is a compilation function? So I give two figures, I mean, one for the time interpretation and one for the space interpretation. And later on, I will focus on time, but everything is similar with space. So you have a profile, which with the time interpretation, you have an initial profile, I mean, votes that you have so far. You compile these votes into sigma p, which is much smaller than p. This is the minimal information you need to store from p. This is a compactification of p. And once the rest of the profile, or, is known, then you can compute the outcome by applying another function, rho, to sigma of p and or, and you get the same outcome as if you had applied the voting rule to p union or. And this is very similar for space, but then you have symmetry between the different districts. Okay? And we say that function sigma is a compilation function for f, if, so I'm extending just the time interpretation, if there is such a function rho, such that rho of sigma p or...
I did not switch slides.
Sorry?
You're still on the first slide, you realize that, right?
No. No. Okay.
We're all seeing the title slide.
Aha, so what happens?
We're sharing the wrong window, I suppose.
Aha. Dominique, you want to come to my office?
Maybe just reshare. Try again. Oh yeah, now we see a different slide.
Okay.
Yeah, very good.
Okay. Full screen. Okay, so you didn't see that one?
No.
Ah, okay. Well, okay, I let you read that one. Okay, I said everything already. I leave it for 20 seconds, 30 seconds.
We understood this, okay.
You're very
okay. Okay, and that one is important. Okay, so with the time interpretation, then you have the initial profile that you compile here, okay, into sigma of p, and then once you know the rest of the votes, then you're able to compute the outcome by applying a function rho to sigma of p and or, and the result is the same as if you had applied the voting rule f directly from the profile without compiling, and it's the same for space, but it's the symmetric version. Okay, and we say that such a function sigma is a compilation function. It is a compilation function provided that there exists a function rho, such that you can compute the outcome from sigma p and or. Okay, and an example, take the Borda rule, for instance. So a compilation function, a very intuitive compilation function, is just store the Borda score, the partial Borda scores from P, okay? So if you have the partial profile P, you just compute the partial Borda scores from P, okay? This is the vector of Borda scores. And of course, this is obvious that it is enough to compute the winner once you know OR, okay? So once you get OR, you just sum the Borda scores for the sigma p that are stored in sigma p and the Borda scores for OR, and you get the total Borda scores, and you can compute the winner. So, so this means that the collection of the Borda scores is a compilation function. It doesn't prove that it is the best compilation. Okay? What does it mean, the best compilation? Well, first, I mean, if sigma is a compilation function for a voting rule F, then size of sigma is the number of bits that you know, the worst case number of bits that you need to express sigma p, okay, for all profiles p. And then the compilation complexity of voting rule F is the minimum of the size of sigma for all compilation functions sigma for F, okay? So it's, and in that case, we say that sigma is an optimal compilation function. So in other words, C of F is the size of the optimal compilation for F, which is the minimal space needed to compile P. Another important notion is equivalence profiles, equivalent profiles for a voting rule. So we say that two partial profiles P and Q are F equivalent. F is a voting rule. If for every profile OR, we have F of P union OR equal F of Q union OR. So for instance, if we take these two profiles, you see that their partial Borda scores are the same. So whatever you add afterwards, I mean, the outcome will be the same. So they are Borda equivalent. These ones are not Borda equivalent. And the proof for that is that we find a profile, remaining profile OR, which is this one, such that if we add it to P, we get an outcome. If we add it to Q, we get a different outcome. Okay, so this is a proof that that P and Q are not Borda equivalent. So the key result, actually, which was not new in the paper, I mean, which was known from the area of one-round communication complexity, says that, but reformulated for voting, says that if the equivalence relation for F, the F, I mean, this equivalence relation here, as G and M equivalence classes, then the compilation complexity of F, that's an F here, is exactly the logarithm of this number of equivalence classes, okay? So easy consequences are that first, I mean, for any F, C of F is bounded by n log factorial M. If C is anonymous, then I'm going quickly here because this is simple and I want to show more interesting results. Okay. If F is anonymous, then we also have this other upper bound. If you have a dictatorship, then log M, the compilation complexity is log M, and of course the compilation is 0 if and only if F is constant. Okay. Okay, so now let me give a few different rules or family of voting rules, and that will be more interesting. First, positional scoring rules, okay? So if we take a voting rule Fs induced by a scoring vector S, then we can prove that P and Q are equivalent if and only if the partial scores are the same for all votes, which is what the intuition says. Okay? Which means that the optimal compilation is exactly to store the partial scores. Okay? And the number of equivalence classes is just the number of ways of distributing these scores to candidates. So of course, we get a different result for plurality because the total plurality scores sum to n, and Borda where they sum to something in the order of nm squared. Okay, now tournament solutions. So if let's denote by MP the maturity graph for P, and if F is based on the maturity graph, then we may wonder whether M, the maturity graph itself, is a compilation for P. And the answer is no, because knowing the maturity graph is not enough to allow us to determine the maturity graph of P union OR. For this, we need the pairwise majority matrix or the weighted majority graph. And actually, this pairwise majority matrix is a compilation for F. But is it optimal compilation? Well, it depends on the rule. Sometimes not. I mean, a constant rule is based on the majority graph, and of course, I mean, and of course, I mean, here the compilation is just nothing. Okay, so the compilation complexity would be 0. But now, if F is Condorcet consistent, then we have this reverse direction. Okay, if P and Q are F equivalent, then the pairwise majority matrices are equal, which means that if F is a tournament solution, then we have this equivalence. Okay, P is equivalent to Q if the pairwise majority matrices are equal, which gives us a bound of communication complexity, an exact bound of compilation complexity. Well, for weighted tournament solutions, okay, there should be a weighted here. This is very similar. We need the pairwise majority matrix and nothing else, and the bound is the same. Okay. Now, plurality with runoff. So P and Q are equivalent for plurality with runoff if and only if the distribution of the tops, I mean, the number of voters who rank X on top of their vote is the same, and this has to be the case for all X. And the weighted majority graphs, I mean, pairwise majority matrices are the same. The reason is that we have to be able to compute the two finalists. So this is why we need to store all the plurality scores, the partial plurality scores, and we need to be able to know which of the two finalists in the winner. And for this, we don't know who they will be, who the finalists will be. So we need to store the pairwise majority matrix. So the optimal compilation is the plurality scores plus the pairwise majority matrix. And this gives us the exact bound, an exact bound on compilation complexity. One more, which is more interesting, STV. So STV, we need to introduce these two notations. I mean, if Z is a subset of candidates, we take a profile P and we say that P minus Z is obtained from P by removing all candidates in Z. Okay? And then N top P minus Z, X is the plurality score of X in P minus Z. Okay? And then we have this result that P and Q are STV equivalent if and only if for all subsets of candidates Z and all X not belonging to Z, N top P minus Z X is equal to N top Q minus Z X, which means that the optimal compilation for STV is the connection of all these numbers N top P minus Z X for Z is a subset of X and X does not belong to Z. Okay? We were unable to have an exact bound of this. We have an upper bound and a lower bound that do not coincide. Okay, if you find an exact bound, you're welcome to publish it.
Jérôme, the word optimal on that slide is not actually optimal.
It is optimal, but we do not have a bound on the cardinality.
Ah, I see.
What is not, yeah, what we are missing is the exact order of magnitude of the cardinality. Which was actually, we were interested in these cardinality bounds at the time, and I would say now I don't care much. I'm not sure. Yeah, I don't know if my co-authors agree. Last slide. I mean, no, there will be. Just one slide after that. Okay. Two conjectures, Young and Dodgson. I'm not going to give details for that, but we have sufficient conditions for the equivalence relation of Young and Dodgson, but we don't know whether these conditions are necessary. So we suspect that it is not easy. Actually, we tried. Yeah. So if you like to solve the problems, please do and tell us and publish it and tell us. Yeah. Last slide. So that was the talk. I mean the paper the talk was based on. There was also this paper published 1 year after, where they gave more results, and also they considered a more refined framework where compilation complexity depends also on the number of remaining voters. And in 2011 we had another paper about compilation where we have a trade-off between compilation and communication. It's a little bit difficult to explain in 5 seconds, so I invite you to read the paper, okay, which has received even less attention. Okay. That's it.
Thank you, Jérôme. Let's unmute and give Jérôme a round of applause. Vince, you made a comment in the chat. Is that something you'd like to talk about?
Yeah, sorry, it was just a comment that the problem that Jérôme had introduced actually turned out to be useful for other algorithmic purposes as well. So I just wanted to point that out, that there's even more motivation for this problem.
Oh, thanks. Yeah.
Carl Dieter, I didn't quite understand your question. Did you want to articulate it?
But was it a question, Vince? Or was
it has a question mark at the end.
It was just praising Jérôme.
Okay, yeah. You mean okay, you're referring to the question in the chat.
Yes. Should A get 4 votes in P is the question.
That was just, I think, a typo on one of the slides, so not important.
Okay. So Peter, you had a question.
Yes, I'm puzzled about whether it's possible to come up with a voting scheme where compilation basically doesn't help. So your communication complexity basically is the upper bound of what it can be.
You mean a rule where the optimal compilation will be the identity? Well,
yes.
You cannot compile. That would be a strange rule. You can surely come up with such rules, but that would be a strange rule. I cannot give you an answer right now, but there are certainly such rules. Yeah, a rule that you have to, like, I mean, the voting rule is very specifically defined for each profile. Okay. So you
No, I was puzzled, for example, whether single transferable vote would be close to such a rule, but you've looked at that and evidently the answer is negative there.
No, you can compile significantly. I mean, the compilation is a little bit large, but still, I mean, significant.
But it's not yet close to the upper bound.
I've seen Vince's comment about the compilation is useful for backward induction in stackable voting games. Yeah, that's right, and I had totally forgotten about that. Yeah.
Good, thanks.
Jérôme, are there any obvious links between this type of complexity and other questions such as resistance to manipulability?
I would say no, but it's heavily related to communication complexity, where you design communication protocols for actually elicitation protocols. But the difference is that what we do is one shot. Actually, you just, I mean, you do not interact you do not really interact with the voters. But with the resistance to manipulation, I do not think there is an obvious link. At least I can't see it. Yeah.
I would have a question which is a bit related, whether one could this compilation complexity is a way of defining a sufficient statistic, as it were, for a sub-electorate. And one might ask the question, to what degree can I estimate the outcome for, let's say, from a randomly sampled sub-electorate, the outcome of the entire rule? What do I need? That would be more statistical version of it. My question simply is there some usefulness in relating to these two problems? That is, there in one problem there could be simple sufficient statistics like a plurality count of the subgroup. In others, for the single transferable vote, that would be harder to say what the sufficient statistics would be. And there may be.
Yeah. If I understand well, so you want to go beyond compilation by compiling even more, by taking some risks.
That's right.
Never thought about that. So I have no answer. Yeah, it's certainly doable, but I've never thought about that.
if I may add something here. I think that there is a work by Nimrod and some colleagues on distributed monitoring of voting rules, which seems to be related to what you're mentioning now. Yeah, I can't. I will post the reference in the chat, but I think it's related to that.
Okay, thank you, Jérôme. I think it's time to move on to the last speaker of today. Hervé, you can share your slides now. Hervé Moulin will be speaking on an efficient and almost budget-balanced cost-sharing method, games and economic behavior 2000.
Excuse me. Yes, sorry.
Looks good.
Okay. All right. So can I go?
Yes.
Yes,
Okay.
you're on.
Yeah. So this is a classic mechanism design paper. Classic in the sense that it uses the standard concept, but less classic in the sense of the particular problem to which it is applied. It comes from this paper in Games and Economic Behavior 2010. So it's about the simplest cost-sharing model with non-trivial questions you can think of and continuous variables. So you're going to have a one input, one output cost function or production function, depending on how you interpret. Here, I will interpret it as a cost function. 0 at 0, increasing convex, and the average cost goes to infinity. So, all right. And each agent is going to demand a certain amount of the output. That's going to be his strategic variable, if you want. And he will have to pay some amount of input. And you can think of input as money. The balance of the cost is simply that the sum of the payments must be equal to the cost of serving all these demands. Okay, look at the notation: Y sub capital N equals C of X capital N. Important to keep in mind here is that the amount of the amount of output I demand is non-negative, but my share can be positive or negative. You will understand, I will explain later why this actually is important. Example, standard, contest, tragedy of the commons, etc. I'm sure you all see, the type of situation. There are many, many games. Agents utilities are standard quasi-linear. So each agent has a concave increasing utility for the output measured in money. So therefore, my utility for the output VI of XI, if I receive that amount of output, minus YI, which is what I pay. Okay. So, all right. Now, the object of study is a cost-sharing rule, namely optimal design of cost-sharing rule according to certain standard objectives. So sharing rule is an object phi, which takes as input the list of demands by the n agents, x1 to xn, and outputs a vector y of cost shares. Remember, y could be negative, and the sum of the y's, namely the sum of the phi I of x, has to cover the cost. Nothing mysterious there. So I repeat that thing. And at each profile, if you fix the profile of utilities and the rule, you have a game. You have a game in which is like a demand game or tragedy of the common, whatever, where you ask for a certain amount of output, you take into account what the others are doing, and based on that, that will influence your cost shares, and that influence your demand and so forth. I mean, the standard situation. What is the design problem? Can we find some cost-sharing rules in which all the Nash equilibria of the demand game for any specification of the utilities in the domain I described. So all the Nash equilibria will be first production efficient. Namely, they will result on the optimal production irrespective of monetary transfer. In other words, the X star, which is X1 to Xn for each agent, will maximize the sum of the utility, the surplus to consumers minus the cost. Okay, that's objective number one. Objective number two, budget balance. So yeah, I realized I made a silly typo before when I was saying the cost sharing rule will be budget balanced. No, in fact, I'm going to have to put water in my wine on that. So budget balance is the ideal, the holy grail, and in fact, you have to compromise. But we are not there yet. What I want you to see now is that what I'm doing here is exactly what the classic VCG mechanism a la Green Laffond are trying to do in a more general context of social choice with monetary transfers, where they look at achieving efficiency in the choice of the public outcome, whether it's a private allocation of goods or anything else, and also to a set of transfers which are balanced, for instance, balanced to zero. So it's very much in that spirit. What's the difference? The difference is here, I'm looking at the demand game where what your message is your XI, what you want. So you could say, well, according to the revelation principle, everything you can do there, you can do with a mechanism where an alternative, but a fundamentally equivalent mechanism where you would reveal your entire utility function. And the point of the approach is to say, of course, that's correct, but unrealistic. Who cares for a mechanism in which you are asked to reveal a full utility function, which can be a very complex object. So the whole, the high level motivation here is we have to stay simple and staying in the realm of actual demand game where you just adjust your demand. That's realistic. I mean, that's the axiom. All right. So now let's see how far we can go. There are three theorems here, and they are actually all quite technical. I mean, this is a paper I like a lot because the proofs are long and non-trivial. I mean, not fabulous, but okay. So first theorem will remind you very much, if you know VCG mechanism, of the classic characterization by Green Laffond, by Holmström and company. Look at this. If the cost sharing method takes the following form, my cost share is the total cost, my cost share given the vector, the profile of demand, is the total cost of serving all the demand minus some amount, which is actually a completely arbitrary function of everything else except my own demand. So here, HI is an arbitrary function of all the other demands and the cost function. So that defined a very large class of cost sharing rules, sorry, because the choice of HI is enormous. But look at the consequence of that form. At least one Nash equilibrium of each demand game will give you the production efficiency. So already just having this form gets you somewhere near production efficiency. And the reason is completely one line. Why? It's because the surplus function, sigma of VI xi minus CXN, is a potential for this game. Okay, the demand game, the strategic demand game, has a potential function, the obvious one, which is the surplus. I mean, this is a one-line verification. Of course, I don't do it here, but it's obvious, and therefore, one of the Nash equilibrium is the one that maximizes this surplus. All of the maximizing the output demand vectors which maximize the surplus are Nash equilibria. The converse statement also holds if you are not in this class, then it will be that at some profiles there will not be no Nash equilibrium which is production efficient. So in that sense, you are stuck with that class, and so far we are really in spirit following the VCG thing. Now, here is a first interesting and a bit surprising thing in the theorem, that if you actually know that your function is differentiable, if your cost function is differentiable, and the rule is one of those I just described, then your Nash equilibria will only catch production efficient outcomes. You will not have some inferior ones. But if the cost function is not differentiable, I mean with a kink, well, unfortunately, then you will catch some production inefficient Nash outcome. So that's interesting because it tells you, well, I mean, your model of a cost function, well, and of course it's a model, it's an approximation, better be smooth if you want to have good properties. So let's test this thing on one class, which is the most natural one, which is also well known, etc., which sometimes is called the incremental cost sharing rule. And that's, of course, an element of my class reminiscent of the one called in the VCG the pivotal mechanism, right? What is my share in that cost sharing rule? Well, it's simply the marginal cost of including me. So it's the cost of serving everybody minus the cost of serving everybody but me, okay? So, and if C is differentiable, the nice properties of before hold. And moreover, within my class, which is very general with very general HI, my incremental rule is characterized by a property which is very natural, which is that if you don't demand anything, you should not be charged. If xi equals 0 must result into you paying nothing, then it's also a one-line thing that the only possibility in my class is this one. So it's a very obviously prominent rule. So why will I dismiss it? I will dismiss it because its lack of budget balance is catastrophic. Catastrophic in the following sense: the lack of budget balance, which is this quantity, n minus time the total cost minus this sum here, will eat up the entire efficient surplus when the number of agents grows large. And when I say will eat up, I mean, you know, I take a worst case ratio of the between the budget surplus. This thing always creates a budget surplus given the convexity. So between the budget surplus and the actual total maximal efficient surplus that you have in the economy, this ratio goes to 1. When you take this worst case, meaning that you know, you essentially leave nothing for the agent. I mean, it's fine from the point of view of the designer if the agents can be made as you know, slaves who don't get any benefit. So that's the thing. We want now to get closer, if possible, to budget balance. Can we do that? You remember that in VCG mechanism, it's a no. I mean, it's a very classic and very sort of primitive result. Here, the answer is not no. The answer is a small yes. Look at this. If C is not a polynomial of degree at most n minus 1, then no rule in the class can be budget balanced. However, if C is a polynomial of degree at least n minus 1 and satisfies all the other properties, so for instance, the main example of such polynomial would be polynomial with positive coefficients, because then you have all the convexity and increasing, but there are others. Then there is a unique anonymous and budget balance rule in that class. And this is the object of the paper, is that there is this canonical animal that's come out, which I call the residual cost sharing rule, and which has a certain combinatorial expression that, of course, given the time constraints, we don't have time to comment above, just to say that it's vaguely reminiscent of potential, like the potential for cooperative games, except that, of course, here this is the share of agent I. So the term in the sum here takes into account the cost of coalitions not containing I. So it's a combinatorial expression like that. No further comments. But look at an example. For n equal 2, it's nothing more than the incremental method. But for n equal 3, it starts already being different. And notice that already at n equal 3, you have a situation where agents can be and will be subsidized. If I am agent 1 here, and this is my cost share, and you put x1 equals 0 in this expression, you can see that immediately that gives you c of x2 plus x3 minus 2 times c of x2 plus x3, so minus c of x2 plus x3, plus c of x2 plus c of x3. So because c is convex and starts at 0, c is super additive, so this number is negative. So you are systematically subsidizing the one who demands nothing. Is that really absurd? I believe no. I mean, you know, the fact of the matter is we are sharing a technology with increasing marginal cost. So the person who abstain from using is welcome, is very welcome by the other. So there is only the issue underlying in the background that if you have to check the identity of the participant, that they are legitimate co-owner of the technology. Otherwise, many people will want to participate in the mechanism and ask for no output. But you see that it's not absurd, and in fact, it will allow us to do something, to have some good methods. 2 additional properties which are normative property that we really want. One is voluntary participation, telling you that if you don't demand anything, then that you could be subsidized, but you are not going to be taxed. I mean, that would be really a bit rich.
Right. Okay. Oh, we have to wrap it up pretty soon, I think.
Yes. 1 minute. 1 minute, okay?
Yes.
Okay. Ranking is if I ask less than you, I pay not more than you, okay? And they are not always met by the residual star rule, but they are sometimes met by some specific class of method, such as totally monotone function, again, functions with all the derivatives being non-negative, and probably also, though this is only a conjecture, by generalized power function, namely power functions with power greater than 1 and their positive combination. So that's why I like this method. Thank you.
Okay, let's unmute and thank Hervé. Dominic, I wonder if you're willing to make the announcement about next month's seminar before we turn to the questions, just so we make sure not to violate the 10:30 rule.
Okay, so next month we will meet again and we'll have another edition of the Oldies but Goodies session. That will be on the 19th of May, and we will hear from Annick Laruelle, Lirong Shah, Chef Mayer, and Clemens Puppe. I hope to see you all there. This will be a week later than usual to make space for Amos.
Okay, and so now we have questions. Does anyone have a question?
Klaus
would pose a question, namely how you would relate or compare your approach to another one to achieve exact balance and only approximate efficiency, which would be by randomly selecting one agent and giving that agent the surplus of the game played among all the other agents, ignoring his demand. And if you randomly choose it, so each time you underproduce because you ignore the demand of one agent, but at the same time you have budget balance because always that agent left out gets all the costs.
Yeah, you could even, I think for this kind of method, you could even take away the randomness and just say that, you know, you do a mental experiment of all the production and then you average, or
that's right.
I mean, absolutely, this is another route which in fact is, I think, much harder to explore, where you impose budget balance and then you try to look for those in which the lack of production efficiency is as small as possible. I mean, as you probably know, I mean, even in the context, very simple context of assigning one indivisible object between n potential recipients, only now we start seeing papers which systematically go to really look at strategy proof mechanisms which are not efficient, and then how close can they be to efficient. So here it's the same thing as you said. I mean, you have Nash equilibria which are not quite there. And if you could say that their price, the price of anarchy is very small. I have done personally some computation for some of these classic methods, average cost pricing, the serial cost sharing, and some estimation of the surplus loss. Unfortunately, what you find is that with a large number of agents, those things converge to zero, converge to total elimination of the surplus, but not very fast. So, but I completely agree. I mean, this is a route that must be explored as soon as we find good approaches. Yes, that's a very good point.
We have time for perhaps one last question. Okay, if there are no further questions, let's another round of applause for all the speakers. Unmute. And I'll be happy to see all of you in about a month.
All right. Thank you very much for Bill for this very original format. I enjoyed it. I hope other people did.
Yeah, thank you.
Bye.
Bye-bye.